So you see problem 7.2 on your screen now. This problem is closely related to problem 5.1, and if you've not looked at problem 5.1, I recommend that you do that before trying this one here. So let's look at this problem. We are given model matrices A, B, and C, and an infinite horizon LQ cost. Now we're asked to first compute the transfer function from u to y and then use it and the spectral factorization to find the optimal closed loop eigenvalues and the optimal state feedback gain. Now I would like to take this opportunity to talk a little bit about spectral factorization um, and give it an interpretation from the point of view of Hamiltonian system, and that's why I recommend that you have a look at 5.1 if you've not done already. So the Hamiltonian matrix is given by this block form as here, and what we know is that the closed loop optimal eigenvalues are the stable eigenvalues of the Hamiltonian matrix H. We also know that if the system is controllable and observable in the sense of the cost Q being factored as C transpose C, then the Hamiltonian matrix has exactly n stable eigenvalues and exactly n unstable eigenvalues and no eigenvalues on the imaginary axis. So now we need to find the eigenvalues of the Hamiltonian. We can do that by solving the characteristic polynomial given here. Note that this is the same as the poles of the transfer function Si minus H inverse. So this is nothing but again the poles of the transfer function corresponding to the system x dot, or let's call it z dot equal to hz. Now we saw in problem 5.1 that this system can be represented as shown in this block diagram. Now we will consider for simplicity just the single input single output case. So let G of S be represented as P of S over A of S. So what we have here is the closed loop G of minus S transposed times G of S with negative feedback. And let's also assume that R can be represented by rho because now it's just a scalar. So we have, instead of minus R inverse, just 1 over rho. So now we can write the poles of the closed loop as roots of 1 plus 1 over rho G of minus S transposed G of S equal to 0, which basically then means that the poles of the closed loop, which corresponds to the Hamiltonian, so we can just say that the eigenvalues of Hamiltonian can be found out by solving for the roots of this equation. Now because it's scalar, I omit the transposed, and this is nothing but the expression that we obtained from spectral factorization, which is A of S times A of minus S plus 1 over rho times P of S times P of minus S equal to 0. So that's also a way to observe how the spectral factorization result can be seen as coming from the Hamiltonian system. Now let's try to use this to solve our problem. We have A given by 0, 1, 5, 0, and B given by 0, 3, and C given as 1, 0. So we can just write down the differential equation governing this, which is y double dot equal to 5y plus 3u. You can check that this is true, and now we can just calculate the transfer function from here as g of s given by 3 over s squared plus 5. So this means that p of s is 3 and a of s is s squared plus 5. So b of minus s is also 3 because this is a constant, and a of minus s is also the same because we have s squared. So then by using the spectral factorization result, we have a of s times a of minus s plus 1 over rho times p of s times p of minus s equal to 0, which means we have s to the 4 plus 10 s squared plus 25 plus 1 over rho times 9 equal to 0. Now note from the cost that rho is 1 because that's the factor multiplying the u squared term. So we have the fourth order polynomial given by this expression. And now we can solve for s. So we can get the roots of this equation, perhaps by using MATLAB. And we know that the stable roots of the Hamiltonian are the optimal closed loop pole locations, and therefore the optimal closed loop poles are minus 2.33 plus minus 0.64 I. Now let's call them P1 and P2 for simplicity, because now we need to calculate the gains. So the closed loop system, the closed loop A matrix would be given by this, which is then 0, 1, 5, 0 plus 0, 3, F1, F2, which is nothing but 0, 1, 5 plus 3F1 and 3F2. So as we did before, we can, so this first of all is the closed loop dynamics. Now we can get the transfer function or the characteristic polynomial by writing down the differential equation quickly, which is y double dot is equal to 5 plus 3f1 y plus 3f2 y dot. That would give us the characteristic polynomial as s squared plus 5 plus 3f1 y plus y dot, s plus 3f2 equal to 0. Now we also know that the optimal closed loop poles are at P1 and P2. So we can have this equation to solve for f. And if we do that, we get something like this. And that's it for this problem. Thanks a lot.